Hi there guys, so today we're going to talk about forces and Newton's laws of motion. So there are three laws by Newton: the first law, second law, and third law. Why are we starting with the forces? Forces are the agents of motion, hence for us to be able to understand the Newton's laws of motion, we have to first understand what causes motion, and then we will move on to the Newton's laws of motion. The Newton's laws of motion enable us to understand motion and make predictions. So let's start with the forces. We can actually define a force as any kind of push or pull on an object. So for example, if you are in your class and you want to move from the front and go and sit at the back, you can actually apply a force, which can be a pulling force or a pushing force, on your desk and move your desk from point A at the front to point B at the back. For example, if you want to move your table from point A to point B in your class, then you can actually apply a pushing force or you can apply a pulling force in the second scenario. In physical sciences, we represent a force using the symbol F, which is a capital letter F, as you can see. And the SI units of force are newtons, represented by the symbol N. These obviously are named in honor of the man himself, Sir Isaac Newton. Another thing that we should know is that force is a vector quantity, and since it's a vector quantity, that means it possesses magnitude or size and direction. Since forces have magnitude and direction and they are vector quantities, that means we can actually represent them using arrows. And when we use our arrows, the arrowhead represents the direction of the force, and then the length of the arrow represents the size or the magnitude of the force. This is very important in trying to find the resultant forces using the graphical method. For example, if you want to represent a 10 Newton force, you can actually represent it using this arrow. However, if you want to represent a 5 Newton force, then you can represent it using the below arrow. As you can see from the two arrows that I have just drawn, the first arrow, which represents the 10 Newton force, is actually longer than the 5 Newton force. In actual fact, the 5 Newton force is half the 10 Newton force, because 10 newtons is twice the size or the magnitude of 5 newtons. In as far as the direction is concerned, you can also see that both forces are in the same direction. In other words, they are all in the easterly direction, or to the east or to the right. If I'm to draw another different force just besides the one that I've just drawn there, for example, I could draw my vector like this, and this will be 10 Newton, and then draw another vector like this representing 12 newtons. In this case, the first vector that I have drawn is 10 newtons in the west direction, and then the 12 Newton force is also 12 newtons in the west direction. So this is a way that we can actually represent vectors. We can also actually represent vectors using directions like this, and in this case this will be 5 newtons downwards. Now let's move on to different types of forces, and as you can see from the flow diagram, there are two types of forces: contact forces and non-contact forces. In contact forces, the two objects that are interacting will be in contact. In other words, they are touching one another. Whereas in non-contact forces, the two objects interacting are not touching one another. They exert forces on one another from a distance. We are going to look at examples of contact forces and examples of non-contact forces. So, the first example of a contact force is the normal force, represented by capital letter N or F and subscript N. The second example of a contact force is frictional force, represented by a small letter F or capital letter F and subscript small letter f. The third example of a contact force is tensional force, represented usually by T or F, capital letter F and subscript T. These are the most important contact forces that we are going to be looking at or meeting in our calculations and our diagrams of forces acting on objects. Now, moving on to the non-contact forces. The first example of a non-contact force is an electrostatic force between two charged objects. So if we have two objects that are charged, then they exert electrostatic forces between themselves. The second one is the gravitational force. Excuse my handwriting. This force is between two objects that have mass. The third force is the magnetic force. These are forces obviously between two poles of a magnet. Now, let's look at the normal force. If you place a book on a table, then that book exerts its weight on the table. And in return, the table is going to exert an upward force on the book. Otherwise, the book would sink into the table if there is no force that is counteracting the weight. That upward force that is exerted by the surface of the table onto the book is the one that is called the normal force. And the normal force is always at 90 degrees or perpendicular to the surface which is exerting the force to an object. So, in other words, or in simple terms, we are saying the normal force is the force that a surface exerts on an object in contact with it and is always perpendicular to the surface. This normal force will be equal to the weight of the object if ever the object is on a horizontal surface, which is not going to be true if the object is on a sloping surface. In other words, if we put the book on a sloping surface like this, then the weight is not going to be equal to the normal force. Remember, we said the normal force is always perpendicular to the surface. But I'm going to explain this in further details very soon. Now, let's move on to frictional force. Frictional force can also be called shear force. If you look at this diagram here, you can see that this person is applying a tensional force to the left on a box, and the surface between the box and the ground in this case experiences a frictional force or friction force. And as you can see in the diagram here, the frictional force is parallel to the surface between the two objects. And this is key, especially when you're going to be drawing free body diagrams and force diagrams. The frictional force is always going to be parallel to the surface of the two objects. Again, if you look at these two diagrams, the purple box and the green box at the bottom, if ever a pushing force is applied on the purple box, there is going to be frictional force between the two surfaces of the purple box and the green box. And again, the frictional force you can see is parallel to the surfaces of the two boxes. The same applies to a person who's pushing a wardrobe. The frictional force again is parallel to the two surfaces, the bottom surface of a wardrobe and the ground at which the wardrobe is sliding on. So by definition, we can say frictional force is a contact force that opposes motion of an object and which acts parallel to the surface. It's always parallel to the surface. Now, let's go back here a bit. We also have a different type of frictional force called air resistance. For example, if you are walking in a park, an open park, and you're walking in the opposite direction to a wind current, you're going to feel the wind applying a force in the opposite direction to the direction that you're walking towards. That resistance to your motion is the one that is called the air friction. In this example here, a person who is cycling also experiences frictional force between himself and the air, and secondly between the tires of the bicycle and the ground, in this case the gravel surface. And again, the frictional force in this case between the tires and the gravel road is going to be parallel to the surface of the gravel. In this case, it's going to be called rolling friction, because the wheels of the bicycle are actually rolling, not sliding. On a slope, the frictional force also is always going to be parallel to the surface. Now, let's look at those two diagrams. If you look at this slope here, you're going to see that if ever you want to push a box up the slope, you can actually apply a force like this, and as the box slides up, there is going to be friction between the surface of the block and the surface of the slope. And take note, this frictional force is parallel to the surface of the block, even though the force that you might be applying won't be parallel to the surface of the block and the surface of the ground. However, the same applies. The same applies if you are applying a force to the horizontal, like just the examples that we saw. If you apply a force to the right like that, then again the frictional force is going to be parallel to the surface of the ground and the box in this case. The second thing is the frictional force also always opposes motion. This means that the frictional force is always in the opposite direction to the direction of motion. There are two different types of frictional forces. There are two different types of frictional forces. We have static frictional force and dynamic or kinetic frictional force. So you might have guessed static frictional force is the force. So you might have guessed static frictional force will be the force that is experienced by objects that are in contact and at rest. The objects are not moving. For example, if you have a box and that box is in contact with a ground and it's not moving, then the force that is going to be experienced between the surfaces is going to be called static frictional force with a subscript S for static. Remember, static means at rest, just like static electricity is electricity at rest or electric charge at rest. Now, dynamic or kinetic frictional force, if you make a clever guess, you would say obviously is the frictional force that takes place when you've got two objects and they are moving relative to each other. So if you have a box and that box is in motion, then in between the two surfaces, the frictional force is now called dynamic frictional force with a subscript K for kinetic. So this is kinetic frictional force and this is static frictional force. Static frictional force happens between objects that are at rest in relation to each other, and kinetic frictional force takes place when one of the two objects is moving relative to the other or both are moving. Now, to actually understand this, we're going to perform an investigation theoretically. So in this investigation, we are going to start with an object that is at rest. If you have an object at rest on a surface, remember we just said that object is going to experience a frictional force, but it's not automatic that the object is going to experience a frictional force. If the surface is horizontal like this, in other words, if the surface has a zero gradient, then that means that this object has zero static frictional force and zero kinetic frictional force. Remember, we defined frictional force in general as a force that opposes motion and is always parallel to the surface of motion. So in this case, there is no applied force, hence there is no frictional force. For frictional force to manifest, then there should be an applied force. So if we apply a pulling force, for example, of 5 newtons, if ever this 5 newtons is not big enough or large enough to pull this block, let's say 20 kg block, then that means this object is not going to move. And since it's not going to move, then that must mean there is a force that is actually opposing that 5 newtons. Otherwise, if there was no force opposing the pulling force, then this object would have moved to the right. We can safely say there is a opposing force in the opposite direction, or to the left in this case, and that force is static frictional force, because as of now the object is not in motion. And we can safely say that that force, or that static frictional force, is equal to 5 newtons. And in grade 10 you learned that if ever the forces are balanced, like in this case, then if you add the two forces, they are going to give you 0, because since they are vectors, their addition will be positive 5 plus negative 5 will give you 0, and hence this object is not going to move in either direction. Now, this is step number 1. You should also understand the fact that now if we increase the force to 10 newtons and still the object doesn't move, then that means the frictional force in the opposite direction is also 10 newtons. And I need you to understand something here. The static frictional force has just increased by virtue of increasing the applied force here to 10 from 5. As you increase the applied force, the static frictional force also increases. As long as the object is not yet moving, we still have some static frictional force, which is directly proportional to the applied force. This was step number 2. Now, let's move on to step number 3. We're going to reach a certain point where, after we have increased maybe to 20 newtons, we are going to reach a certain point where the frictional force, there is a certain point where we will reach whereby when we increase the applied force, the static frictional force can no longer increase. And at this point, the object does not move. However, the moment that we exert a little more force, maybe I can say 20.000001 newton of a force in this case, then the object will then start to accelerate to the right. Let me redraw this diagram and explain. Now we are saying we have increased the force to 20 newtons. And since we have increased the force to 20 newtons, however, at this point, the static frictional force can no longer increase. It has reached its maximum value. Hence, on top there, we can write F max to represent that it has reached the maximum value. And any further increase, like I just said, any further increase above 20 newtons, any slightest increase, for example 20.0001 newtons, will result in the object accelerating towards the right. This is when the applied force is now greater than the static frictional force. We'll understand this much more further when we look at the Newton's second law of motion. Now, you should understand the maximum static frictional force that is going to be experienced by an object depends on two very important things. It depends on the normal force and the material of the surfaces or the objects that are in contact. Let me explain. So, you should know that whenever an object have got a large mass, then that object is going to have a larger normal force. And as you shall see, the static frictional force is directly proportional to the normal force. Then that means it's going to lead also to a larger maximum static frictional force. So this is simple and straightforward. We're saying the maximum static frictional force depends on the normal force and the materials of the surfaces that are in contact. And looking at the normal force, we are saying if an object has got a larger mass, then it's going to produce a larger normal force. And that larger normal force, since it's directly proportional to the maximum static frictional force, is going to produce a larger maximum static frictional force. And this makes perfect sense. Why am I saying so? If ever you have got a large object that you want to move, let's say you want to move an elephant and is just lying down, maybe a dead elephant, you want to move it from one place to the other. We all understand an elephant is very heavy. So if you try to push a dead elephant, because of its mass, its normal force is going to be very large, and hence its friction between its skin and the ground is going to be very, very large, and hence it's going to be very difficult for you to actually push that elephant. However, if we compare that maybe to a dead pig have got relatively a smaller mass, and hence it will have a smaller normal force, and that will lead to a smaller frictional force between its surface and the surface of the ground, and hence it will be relatively easier for you to push and move that dead pig from one point to the other. Now let's move on to materials. This is obvious. We can compare the roughness of a material to another material. A surface or a material that is rough is gonna have a higher friction value or a frictional force as compared to a material that is smooth. Now, we just said that the maximum static frictional force is dependent on the normal force. How exactly is dependent on the normal force? You should have heard me mentioning that the maximum static frictional force is directly proportional to the normal force. In other words, if the normal force increases, then so does the maximum static frictional force. If the normal force decreases, so does the maximum static frictional force. So they're directly proportional. For us to be able to eliminate or remove the direct proportionality sign, we have to introduce a constant, and the constant that is going to be introduced here is mu s. So as you can see on the left there, mu s is the proportionality constant and is the ratio between the maximum static frictional force and the normal force. That is, mu s is equal to F max s over n. So you can see, in other words, we're simply saying that this value of mu s is actually the ratio between the maximum static frictional force and the normal. That means each value of mu s is actually unique to each and every surface combination. In other words, if you take glass and wood surfaces, then these two will have a unique mu s as compared to probably glass and granite rock surface. They're definitely going to be different. Glass and granite rock will have their own unique mu s. So this is actually a unique property of materials, and it depends on both surfaces that are interacting. You can see here it's glass and wood and glass and granite, but their mu values will be different. So the value of mu s can only be equal to 0 if there is no friction. If there is no friction between two objects, then the value of mu s will be equal to 0. However, you must know that the values of mu s are only between 0 and 1. In other words, if ever you're doing a calculation and you find out that you get a value that is greater than 0, then automatically you must know there is something wrong with your calculation somewhere. Your values that you're supposed to get are always supposed to be between 0 and 1.
Please note that the coefficient of static friction has no units. Doesn't have any units. Now, there are a number of things that you should understand. You should actually understand that we can formulate this equation where we can calculate the maximum static frictional force. So the maximum static frictional force can be calculated using this equation, and in this equation, as you can see, Fs max represents the maximum static frictional force, and then mu s the coefficient of static frictional force, and capital letter N the normal force. You should take note of two things. The first thing is that when an object is at rest, then its static frictional force is going to be less than the maximum static frictional force. However, if an object is just about to move, then its frictional force is going to be less than or equal to the maximum static frictional force, which is equal to mu s times the normal force. So now, for purposes of calculations, we are going to look at two scenarios. The first scenario we're going to look at is of an object that is at rest on a surface. So this object is going to experience a weight and a normal force. And remember, we can also represent weight as Fg. Alright, so because this object is at rest on a horizontal surface, then that implies the normal force is equal to the weight. And since we know that the weight is equal to the mass of an object times the gravitational force, the mass of an object times the gravitational force, then this also implies that the normal is equal to the mass times the gravitational force in this case where the object is on a horizontal surface. And since the maximum static frictional force is equal to mu s times n, then we can actually substitute for the normal force with mg, meaning that the maximum static frictional force will be equal to mu s times m times g. The second scenario is when we have an object on a slope. So in this case, the object's weight is not going to be equal to the normal force. In other words, we're saying n. Okay, so actually what we have to do here to find the normal force, we have to resolve the weight into its y component, which we are going to call wy, and the x component, which we are going to call wx. And to do that, since we know that this angle between WX and W is theta, we can actually resolve WY and WX. So we can actually form a triangle that looks like this. It's WY, then from there to there, that's WX, and then this will be our W, and this angle theta. So using this triangle, we can actually find our WX and WY from the use of trig ratios. We know that we can use SOHCAHTOA, though we are only going to use SOHCAH because our angle there is going to refer to the adjacent and hypotenuse and opposite and hypotenuse only. Now, sine theta is equal to opposite over hypotenuse, which will be equal to our opposite. In this case, we can see is WX, and then our hypotenuse is the weight, which implies that if you are going to rearrange this part and this part, you are going to see that WX is going to be equal to weight times sine theta. Now, using cos, we know that cosine theta is equal to adjacent over hypotenuse, which is equal to adjacent. We can see it's WY over the hypotenuse, which is our weight. So if we rearrange this and that means our WY will be equal to the weight cos theta. So that's how we resolve to get WY and WX. So it's going to be like this all the time. So just to write it on the diagram, WY will be equal to W cos theta, and WX will be equal to W sine theta. So these are the second equations that we're going to be using when we are using Newton's laws of motion. Right, so now you can see that our normal force, which was not equal to the weight, is now actually equal to WY. And we say WY is actually equal to W cos theta. That means our normal force is actually equal to W cos theta. And remember, we know that the weight is equal to mass times acceleration due to gravity. Hence, substituting in this equation, mg cos theta will be our new equation to find the normal force. And since we know that the maximum static frictional force is the coefficient of friction times the normal force, this implies that our maximum static frictional force becomes equal to coefficient of static frictional force times mg cos theta. That will be our equation to calculate the maximum static frictional force whenever an object is on a slope. Let's look at the example on your left. They say calculate the magnitude of the maximum static frictional force a 600-gram wooden block experiences when it rests on a horizontal plane with coefficient of static friction of 0.5 and is subject to an applied force. So the best way to solve this problem is by drawing your diagrams. Make sure all the time you draw the diagrams to show all the forces that are acting on the object. So in this case, this is question 1. We have an object that is on a horizontal surface and the mass of the object is 600 grams. And we know that mu s is 0.5. Now looking at this diagram, we can see that obviously the object is going to experience weight or Fg, and in turn will also experience a normal force. And in this case, obviously our normal force is equal to the weight because the object is on a horizontal surface. So that means our normal will be equal to the product of the mass of the object and the gravitational acceleration, of which gravitational acceleration is 9.8 meters per second squared. Now, we know that to calculate the maximum steady frictional force, we use this formula whenever an object is on a horizontal surface. So we are simply going to take our values and substitute, but before we do that, either you can calculate the normal force separately, or you can actually expand the equation and say mu s times mg, because the normal is equal to mg. Okay, so now substituting our values, mu s is 0.5 times the mass. Take note the mass is 600 grams. However, we have to convert the 600 grams into SI units, which are kgs. So we should divide by 1,000 to convert them into kgs from grams. Then times g, which is 9.8 meters per second squared. After the calculation, or after computing in your calculator, you are going to get 2.94. And since this is a force, it's in newtons. Okay, now moving on to example number 2, where the object is on a slope of 30 degrees. Again, we are going to draw our diagram. First, this is 30 degrees. So this is our object, and our object is going to have a weight which is vertically downwards and a normal force which is perpendicular to the surface, and of course is going to have frictional force upwards. In this case, obviously, it's going to be static frictional force because the object is not moving. So remember what we said. In this case, our normal force is not equal to the weight, which means the normal force is actually equal to Wy, and that means normal force is equal to Wy, which we said in our previous calculations, or in our previous derivation, Wy will be equal to W cos theta, which is equal to mg cos theta. So we can actually calculate our maximum static frictional force, F max S being equal to, remember this is equal to mu S times the normal, which is equal to mu S times the normal. In this case it is mg cos theta, mg cos theta, and substituting our values, mu S in this case is still 0.5. Our mass is still the same, 600 divided by 1,000 times 9.8. The cosine of theta in this case is 30 degrees, and if we use our calculators, we get 2.55 newtons as our final answer. So I want you to take note of something. In example 1, where the object was on a horizontal surface, the maximum static frictional force was equal to 294. However, the maximum static frictional force on a slope is 255. In other words, the maximum static frictional force on a horizontal surface is always going to be greater than the maximum static frictional force on a slope. This is always going to be true as long as the masses are going to be the same and the coefficient of static frictional force or the surface is the same. That means our maximum static frictional force for the horizontal surface is going to be greater than the maximum static frictional force on a slope. Now, there is one last formula that I would like you to know. If ever we've got an object on a slope with angle theta, then you should know that if that object is just about to slide, in other words, if ever its maximum static frictional force is now equal to Wx. Wx is equal to F max. This is the point where the object is about to slide. In other words, the static frictional force can no longer increase. Then at this point, we can actually calculate the coefficient of friction of the surface using an equation. Nu s is equal to tan theta. For the derivation of the equation, you can actually look at the left side. Right, now we've been dealing with the static frictional force, and now let's move on to kinetic frictional force. So obviously this takes place on objects that are in motion. One very important thing that you should take note of is that always your kinetic frictional force is going to be less than the maximum static frictional force all the time. I will show this graphically very soon. So just like static frictional force, kinetic frictional force also depends on the normal force. In other words, the kinetic frictional force is directly proportional to the normal force. Then if you want to remove the proportionality sign, the kinetic frictional force will be equal to a coefficient of kinetic friction times the normal. One important factor also that we should remember is that another very important thing that we should remember is that the kinetic frictional force is always going to be constant. This kinetic frictional force also is independent of the size of the surface to the velocity of the object. Now, looking at the left graph that is drawn, you can see if you plot frictional force versus an applied force. Remember, we said that for static frictional force to be present, there should be an applied force. If there is no applied force, then there won't be any static frictional force. So if you apply a force, as you increase the magnitude of the force that you are applying, so does the static frictional force. And it's going to increase until a point where it reaches the maximum static frictional force. And at this point, the static frictional force can no longer increase with increase in applied force. And as soon as the object starts to move, the static frictional force is going to decrease. And at that point, when it decreases, it's no longer being called the static frictional force. It's now being called the kinetic frictional force because the object is now moving. And as you can see from this graph, the kinetic frictional force is going to be constant in spite of the applied force being increased. In other words, you can increase the applied force, however, the kinetic frictional force remains constant, unlike the static frictional force that increases with increase in the applied force until it reaches a maximum static frictional force point or magnitude. So this is very important. And also, as you can see, the kinetic frictional force is smaller than the maximum static frictional force, which we highlighted here, that the kinetic frictional force is always going to be smaller than the maximum static frictional force of that object. Very important thing to note. Now, moving on to non-contact forces, we're just going to explain these ones briefly because non-contact forces are not going to be used in our calculations using Newton's laws of motion. So, like we previously said, a non-contact force is a force in which the two objects that are exerting forces on each other are acting at a distance. In other words, they are not in contact with one another. And examples of non-contact forces are the electromagnetic forces between magnets, as you can see in this diagram here, and electrostatic forces between charged objects, as you can also see here. We also have gravitational force of attraction between objects that have masses in this case. Now, moving on to the final thing before we can do proper calculations using Newton's laws of motion. We are going to move on to force diagrams and free body diagrams. These are very important in as far as calculations are concerned, because these tell us the forces that are acting on an object, and these are the forces that are going to result in motion of an object. So the first thing you do before you do any calculation is to actually draw the free body diagram or the force diagram, indicating all the forces that are acting on that particular object. So, what is the difference between a force diagram and a free body diagram? A force diagram is going to show all the forces as they are. In other words, it shows both the pulling and the pushing forces. A force diagram is going to show all the forces acting on the object as they are and the object as it is. In other words, a force diagram will show the pushing and the pulling forces. Force diagrams are going to show all the forces. Force diagrams are going to show the actual object and the actual forces acting on the object. In other words, they are going to show the pulling and the pushing forces as they are. However, a free body diagram is going to show all the forces acting on the object as pulling forces, and the object is going to be represented by a dot. Okay, so we're going to look at examples of diagrams where we can actually draw free body diagrams and force diagrams. So if you're given, for example, an object on a horizontal surface like this one, and they ask you to draw the force diagram, then automatically here the only two forces that are going to be present will be this normal force and the weight. And since we do not have any applied force, that simply means that there is not going to be any static frictional force. So this will be our force diagram. So this is going to be our force diagram. However, if we are asked to draw the free body diagram, then our object, which is that box, we are going to represent it as a dot, and then we will have a normal force upwards and the weight downwards. This will be our free body diagram. Now, however, if for example on this object we do have an applied force F, let's say this object is being pushed. However, if we have a person pushing this object to the right, if you're asked to draw the force diagram and the free body diagram, we can actually draw this like this. And if the ground is rough, then we can also have frictional force. However, our free body diagram is going to be like this. Going to represent the object as a dot, and we will have our normal force and weight and applied force and the frictional force. I need you to take note of the differences here. The first difference is in the object. The object here is represented as the actual box, and here the object is represented as a dot always. And secondly, the applied force is represented as a pushing force here, as it was a pushing force on the person there. However, in the free body diagram, it's represented as a pulling force, and all the forces here, as you can see, are indicated as pulling forces. Here they are indicated otherwise, or as they are. Now let's answer the question on your left there. They're saying draw the force and free body diagram indicating all the forces acting on the block if the surface is smooth. That is no frictional force. So we can see that those two objects are connected. So I'm going to redraw those two objects. So it's very important that you first indicate the forces on the actual diagram that you are. Okay, so obviously the obvious forces that we know that are going to be present are the weight and the normal force. And on the second diagram, the same thing, the weight and the normal force. And of course, we can see here we have an applied force. However, we know that box B is being pulled backwards by block A or box A. Hence, we do have a backward force on B as a result of A. And at the same time, on block A or box A, we do have a force that block B exerts on A, which means it's going to be in this direction like that. So if we are to actually draw the separate two diagrams, or the diagram separately, it's going to look like this. This will be our force diagrams. So we have A here, and then separately we have B here. So like we said, we're going to have our weight, normal force, and tensional force. At the same time here, we are going to have our tensional force. We can call this tensional force for A and tensional force for B. We also have our weight and our normal force and applied force. Applied force. So this will be our force diagrams. Now let's draw the free body diagrams. For A, it's going to be like this. Object represented by a dot. We have the normal force. We have the weight, and we actually have the tensional force of A. And then for B, we have the object represented as a dot, and then we have a normal force, weight, we have applied force, and tensional force B. Great. That will be our free body diagram for object B. Now we can also draw the force and free body diagrams indicating the frictional force. So it's going to be, but because there is friction, then we are going to add frictional force. We are assuming that it's going to move to the right because that's where the applied force is pointing. This is tension and frictional force 2. So this will be our diagrams with frictional force. These are our free body diagrams, and these ones are our force diagrams. Now go ahead and draw the free body diagram for this question and pause the video while you do that, then check the answer later. Now the free body diagram for A is going to be like this. We do have the normal force, and the weight and tensional force. And if ever there is frictional force, then it's going to be the left, but in this question there is no frictional force. And then for B, we have the object, and as we can see, the object is being pulled upwards by the cable or the rope, hence we have a tensional force and also the weight. So those will be our free body diagrams. And one thing that we are also going to see is that this tension on A and the tension on B is going to be equal. Very important in calculations. Now let's move on to the next question. On a slope, on a slope we have got B and A. So the free body diagram for B is going to be like this. We represent the object with a dot, and we have the normal force, which is going to be 90 degrees to the slope, and the weight, which is going to be vertically downwards. And of course, if there's friction, it's going to be down the slope, and we are also going to have tension upwards. And then for the object A, we are going to have again the normal force, which is perpendicular to the surface, and the weight, which is always also vertically downwards. And you can see we have the applied force and the tension going downwards. And if there is friction, then there's going to be friction going downwards. So this will be the free body diagrams for A and B. Now, moving on, let's look at this one. Okay, so now for this one, for object A, we've got the object, and then as usual, we're going to have the weight. And take note here, we are not going to have a normal force because the object is suspended in air. It's not in contact with a surface or with another surface. Hence, the normal force is not present in this case. Rather, we only have an upward force, which is the tension in the cable or in the rope. And the same applies to B. We also have the weight of the object. We also have the weight of the object and the tension upwards. And like we said, those two tensions will be equal. So this will be the end of the lesson. Hope you enjoyed the lesson. Please like and subscribe. Thank you.